My name is Emilio Cardona.
And I'm Andre Chiru.
And today we'll be reviewing Bell's Inequality, the weirdest theorem in the world, Nobel Prize 2022. This video was made by Qiskit, which is an open source software development kit for quantum computers at the levels of circuits, pulses, and algorithms. Now, this might be a company that you've never heard of, but is owned by IBM Computers. As we know, IBM is quite big in terms of quantum computing and some other science branches.
In this video, we will see a very good explanation of the Bell's theorem. However, we would like to expand on some missing essential information that we find that might be beneficial to have in the video. One of the reasons we can say that this information was not included in the video was that they were trying to appeal to a larger audience.
Hi, my name is Olivia Lanes from IBM Quantum, and I'm here today to celebrate and explain the relevance and the excitement around the 2022 Physics Nobel Prize. So just a few days ago, the Physics Nobel Prize for this year was awarded to three gentlemen, John Clauser, Elaine Aspect, and Anton Zeilinger. These gentlemen won the award for groundbreaking research and experiments in quantum mechanics. And all of this research was based upon some original experiments that were done by a gentleman named John Bell, who tragically passed away before he was able to see a Nobel Prize or something of that magnitude.
The experiments mentioned in the video were done in the 1970s and 80s, and they tested the predictions of quantum mechanics against the principles of local realism. One of the most famous experiments is the Aspect experiment, conducted by Elaine Aspect in 1982. In this experiment, Aspect used a setup involving the emission of pairs of entangled photons, in which the polarization of one photon was correlated with the polarization of the other. The experiment involved measuring the polarization of one photon at a time and comparing the results with predictions based on local realism. The results of the experiment showed a violation of Bell's inequality, which is a mathematical expression that describes the limits of local realism in explaining the correlations between entangled particles.
But we're going to discuss it here today and show why the experiments that were built off of John Bell's original theorem are so important. So we have to go back a little bit in history in order to set the stage and the context of why this is so important. So in the 60s, John Stuart Bell was reading the EPR paper, which was a paper written by Einstein and some of his colleagues explaining how they believed that quantum mechanics was an incomplete theory.
So what is Einstein EPR? Einstein EPR paper is a landmark scientific paper published in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen. The initials EPR stands for the last names of the three authors. The EPR paper posed a thought experiment involving two particles that had interacted in the past and were now separated by a great distance. According to the principle of quantum mechanics, the state of one particle cannot be determined without measuring it, and the act of measuring affects the state of the other particle. They proposed that there must be hidden variables that determine the properties of particles, even when they are not being observed. The EPR paper sparked intense debate among physicists, and its implications continue to be studied and debated to this day.
Now, in quantum mechanics, we say there exists this thing called the wave function, which describes all of the properties of your quantum system, and upon measurement, it collapses into a single quantity that was only described probabilistically before you measured it. Anyway, in the paper, Einstein said that quantum mechanics must be an incomplete theory because this could not be possible. This would necessitate things that he could not believe to be true. And so we were either missing something in the theory. Somehow these particles were interacting in a way that we didn't actually understand or didn't have a description for yet, but basically it was not finished. And sometime later, John Stuart Bell was reading this paper, and he sat down and he wrote what is come to be known as Bell's theorem in just a few lines of algebra. He showed that if you only assume two things, those things being local realism, locality, meaning you can't travel faster than the speed of light, and realism, which means that things have definite values whether or not you measure them. So for instance, we always say if a tree falls in the forest and no one is around to hear it, does it make a noise? If the answer is yes, this would be an example of definite realism.
Further elaborate, local realism is a concept in physics that suggests that physical systems have definite properties, such as position and momentum, that exist independently of any measurement or observation. It also suggests that these properties are determined by the physical state of the system and are not influenced by anything outside of that system. Local realism further asserts that these properties can be determined without any action at a distance or faster than light communication. So basically, it's the idea that there is an objective reality that exists independently of our observations or measurements, and that this reality is governed by local interactions between objects.
So he assumed only those two things in his mathematical derivation. And he was able to show that there are certain quantities that you can measure that are bounded by classical physics if you assume only local realism. And essentially, he was able to show, on paper at least, that quantum mechanics was incompatible with any classical theory. So anything that was basically including local realism could not possibly work with quantum mechanics. So now, a few years later, John Clauser came along, and he was reading Bell's theorem. And he thought that this should be something that was able to be done experimentally. So he was able to actually perform an example in the laboratory for the first time, a violation of this equality, and show that indeed nature behaves as weirdly as predicted. And so in essence, Einstein was wrong in his EPR paper. And this led to groundbreaking work later on from Elaine Aspect, who was able to perform even more tests of Bell's inequality and close some of the loopholes, so to speak. And then this led to Anton Zellinger, who was able to show the demonstration for the first time of quantum teleportation.
In the experiment, they created a pair of entangled photons, A and B, and sent photon A to a remote location while retaining photon B in their lab. Then they replaced a third photon C in close proximity to photon B. Next, they measured the state of photons A and C, which caused the entangled state of photon B to collapse into a new state that was identical to the original state of photon A. Essentially, the information about photon A's state was teleported to photon B through the state of entanglement. This experiment demonstrated that quantum information can be transferred instantaneously without any physical connection between the two locations. It's important to note, however, that only the state of the photon was teleported, not the actual physical particle itself.
Which is not what you might think. It's not at all like Star Trek. People are not teleporting across the room. But instead, quantum teleportation is a way to entangle or correlate quantum particles in such a way that you can transfer quantum information from one to another. So in order to really understand why this is so important and why this is so groundbreaking, I want to go back and look at a very specific demonstration of Bell's tests for you. There are, in fact, many different Bell-type theorems that can be shown, but we're going to look at really one specific one today, which is called the CHSH test, or the CHSH inequality. And so what you need to do for this thought experiment is first imagine a person named Alice and a gentleman named Bob, and they're standing some distance far away from one another. And then there's another guy in the middle, let's just call him Victor, and he's going to send a particle to Alice and to Bob at the same time. And Alice and Bob are going to perform every single time this happens one of two measurements. They're going to either measure the x projection or the y projection of this particle. And so you can only measure one at a time. So in order to have a good understanding of the measurements of both, they have to perform this experiment multiple times. And it's important to know that every time Alice receives a particle, Bob also receives a particle. And again, the only thing really assuming here is local realism. So these particles are not moving faster than the speed of light. Bob and Alice can't call each other faster than the speed of light and communicate information, nothing like that. And these particles also have these definite values that are either going to be 1 or -1. Because
The CHSH inequality involves a specific combination of measurement outcomes at Alice and Bob's detectors, which is derived based on the assumption of local realism. Now, what is this assumption? This local realism concept assumes that the measurement outcomes are determined by a local inherent variables, which are pre-existing properties of the particles that are not directly observable, which in this case, she mentions are 1 and -1.
it has to be less than 2 if the only assumptions we are making are locality and realism.
If the measurements violate the CHSH inequality, it implies that local realism is incompatible with quantum mechanics. In other words, the measurement outcomes cannot be explained by local hidden variables, and therefore, the particles must be entangled in a way that violates the principle of locality.
However, let's think about this experiment again, slightly differently. Let's now assume that instead of a particle, just a random object, Alice and Bob are receiving, they are going to be receiving entangled qubits. These are qubits. It doesn't matter how they were entangled originally at the beginning, let's just say that they are. What you're actually going to measure, once you perform this experiment hundreds of times, is that this quantity is going to be approximately 2.8, not 2, not less than 2. We know for sure that 2.8 is greater than 2, which means that if these qubits obey the laws of quantum mechanics, which we know they do, quantum mechanics violates Bell's inequality. It is incompatible with local realism. So either something is moving faster than the speed of light, or these particles do not have definite values before they are measured. And you might be wondering, where does this 2.8 number come from? Certainly, it's greater than 2, and we can understand that it does indeed violate this inequality, but where does this 2.8 come from? And so if you're interested, I challenge you to go online to the Kiss Kit textbook, and the link is linked below in the bio, and to try your hand at this experiment for yourself. And while you might not win a Nobel Prize for doing this, because lots of experiments in this vein have been done at this point, I still think it's miraculous that we have gone in a few decades from an experiment that is Nobel Prize winning to an experiment that you can do, that I can do, from anywhere in the world. So what this showed is that quantum mechanics is even weirder and even more mysterious than we initially thought it was. It's completely incompatible with any classical theory that we can come up with if you assume locality and realism. And reading this, you might think that makes no sense, that's impossible, I hate it.
For example, some of these videos make the claim that quantum mechanics is a purely theoretical concept that has no practical applications or experimental evidence to support it. Well, this claim is simply not true, as the practical applications of quantum mechanics are numerous and have been extensively documented for experimental research. The biggest one we could think of right now is quantum computing, for example, which is being developed in many, many countries. Other misunderstandings that are often presented in these videos include a confusion between correlation and causation, a lack of understanding of the nature of probability in quantum mechanics, and a failure to account for the effects of measurement on quantum systems. A common way they do this is by mentioning that random number generators that are used in these experiments are prone to fluctuations. Basically, they're saying that the random number generators don't generate random numbers. However, scientists take this into account when they do the experiments. These misunderstandings can lead to flawed conclusions that are not supported by experimental evidence.